In this video, we're going to look at how we can do low side current sensing using SEELab. So first I'm going to open the circuit. This current to voltage converter is called. And I have this circuit diagram for a transimpedance amplifier where the input current gets converted to a corresponding output voltage where the amplification is minus into whatever the feedback resistor is. So all that you need is an opamp and a feedback resistor. And we're going to use the PCS output, which is programmable current source, goes from 0 to 3.3 or roughly 3 milliamperes, which is here. And that's going to be our test input. And PCSV is actually the voltage across PCS. So it's internally monitored here. So right now it's floating. So let me add a resistor. I'll first check the value of the resistor by connecting it between sen and ground. And you can see that the resistance here is 1K. And if I just simply connect PCS to ground through that 1K resistor, like so, I see that if I set a current of, let's say, 1.02 milliamperes, I have a corresponding voltage of 1.02 volts because Ohm's law. Okay, V is equal to IR. So current into 1000 gives you this 1 volt here. Fine. So now let's involve this transimpedance amplifier circuit. And it's fairly simple to make. So let me just quickly put pin 6, which is your output, to pin 2, which is your input. So that's your feedback resistor. I need a positive power supply, which I'm going to take from here, plus 6 volts. Then there is pin 4, which is minus 6 volts. Okay, so pin 7 and 4 are this thing. Now, the output of this circuit, pin 6, I'm going to connect to A1. And pin 3, which is your non-inverting input, must be grounded, such that pin 2 becomes your virtual ground, 0 volts. And here, I'm going to connect PCS. So that's my current input. Now the difference that you see from the previous approach and this is that when I set 1 milliampere here, okay, this current is going to flow directly into virtual ground here. Okay, so it's not flowing here, it's basically going through here, but it sees a potential of 0 volts, right? So this this 1 milliampere gives you minus 1 volts, 1.02 roughly volts. So your current is measured as 1.02 milliamperes here using this transimpedance amplifier circuit. But the difference that you see here, there's no PCSV here because there is no potential difference involved. The current is entirely flowing to a 0 potential. So that potential here is actually 0 compared to the previous case where we actually had some potential there. So yeah, that's your very simple 1 op-amp, 1 resistor amplifier. And if you use a very good op-amp with small input offset, you can actually amplify very small currents, like down to nanoamperes. And if you want an even more sensitive setup for measuring current, there is the sensitive current to voltage converter. This is again a slight modification of this circuit where there are 200K resistors and there is 100 ohms to ground. So whenever there is some small current coming here, this voltage must be adjusted such that the potential here becomes 0. Now, in order to adjust this, of course, there is the almost 200K path back, but there's also 100 ohms taking this voltage to ground. So a lot of current goes that way. So you end up getting very high gain. And the sensitivity here, as mentioned, is for every 10 nanoamperes, you get around, minus 1 volt signal. And this LED is used as the input for this circuit. You just simply shine some light on it and you'll get some signal. So the LED is used as a photodiode or sensor. So I think that covers measurement of current. We've covered using Ohm's law, and we've also covered using a transimpedance amplifier. Thank you.